Welcome to Schweitzer Drive, a podcast where we explore what goes on between the generation of electricity and the light switch. Join Dave Whitehead as he interviews the entrepreneurs, innovators, and experts who are inventing the future of electric power.
Hi, I'm Dave Whitehead, and my guest today is Dr. Steve Pekarek. Steve is the Edmund O. Schweitzer III Professor of Electrical and Computer Engineering at Purdue University. Steve is an expert and actively researching a number of topics that I'm really excited about and will bring great benefit to all of us, including predictive power system control and the electrification of roadways. Steve is an active member of IEEE Power Engineering Society, the Electric Ship Research and Development Consortium, and the Advancing Sustainability Through Powered Infrastructure for Roadway Electrification Center, or ASPIRE. Steve earned his PhD in electrical engineering at Purdue University. Steve, thanks for joining us today. I'm really excited about the topic, which is, of course, power system control. There's a lot going on in our industry these days, and I thought it'd be an excellent opportunity to get an expert to talk about the concept of power system control. Going back just a little bit, power systems are changing from large generation facilities like coal or gas and even hydro to a lot more smaller renewable generators like wind turbines or solar panels. So from your perspective, how do these changes in the generation affect the reliability of the grid, or does it?
Dave, thanks for having me. And I guess you would have to ask that question. It depends where it's placed. Certainly, if the large solar or wind installations are placed part of the transmission system, then you tend not to have the issue. And indeed, I think studies have shown that since their increased penetration levels since the early 2000s, there hasn't been a change in reliability of the transmission system. There's regulations, there's the Federal Energy Regulatory Commission, there's the North American Reliability Corporation. They set standards. So from that perspective, there isn't significant concern. I think those have been addressed. I think where the challenge becomes is in the distribution level, where there is less regulation and there are more lower power, as you had indicated, systems being deployed, sometimes behind the meter. And so as a result, there is somewhat unknown, it's less regulated, and so there's uncertainty. And so with uncertainty tends to lead to a change in reliability, a lower reliability. But I think that's, where I can't quantify a number, but I think that's where we're really standing now.
I made a comment that there are more smaller renewable generations. I was actually talking to a utility on the East Coast, and they have over 2 gigawatts of solar that go into their system. And some of these solar plants are connecting in at the 500 kV level. So there's that's a significant amount of solar power being introduced into the electric system. And I gotta believe that from a control side of stuff or power flow, certainly that those represent some unique challenges. Whereas you can expect a thermal plant or something to be generating the same amount of power 24/7. Certainly the solar has challenges at night putting out power, especially if there's no on-site storage, whether it's batteries or pump storage or something like that.
Yeah, exactly. And when you're dealing with at the transmission levels, like I had said, that's oftentimes set by regulatory standards in terms of being able to even present onto that infrastructure. And so having, for example, backups in terms of maybe even a generation plant that supports that, or energy storage that supports that, that's essential. And I think is studied and really implemented to date. The challenges, like I said, really comes when we start to have all of these different solar solar on rooftops, in plants, that it isn't accounted for, and how do you address that?
Yeah, I was down in California a few years ago talking to one of the big utilities there, and what they were seeing was with the so much solar rooftop generation being put on that it was actually starting to affect the transmission system. It was becoming a lot less loaded, right? So they're having some voltage challenges because of all the renewables during the day. They were, not necessarily putting as much energy onto certainly the transmission system, but the demand from the transmission system was going way down during, peak solar times.
Right. And I think there is a push toward trying to get more of the regulatory or standards at that distribution level. And certainly there's the whole smart grid effort initiatives where there is an attempt to do coordinated control at these levels, but that really the standards associated with that I don't think have been adopted and to a level that would support, for example, a lot more integration of those renewables. So I think that's a concern people have and are attempting to address.
Yeah, and regardless of whether you're a big fan of hydro or traditional generation sources, or you're in favor of renewables, whether it's wind or solar, or perhaps even in nuclear, this is happening to the power grid. So what do you see as the benefits or the challenges of all this changing generation on the electric grid?
Yeah, the benefits, initially it started probably with health benefits, and certainly has been motivated by climate change as well. So, you don't have the pollutants, you don't have the greenhouse gas emissions, and so that provided an incentive. There is the additional incentive that you don't have a fuel cost variation, right? You're not sitting there on a market price associated with the cost of coal or the cost of gas. That can be particularly attractive as well. Of course, it also leads to its own set of challenges that we had just indicated, where you need some backup source to support when your wind varies or when your solar varies. And so it's somewhat of a balancing act, and understanding the trade-offs between all of those sources to try to come up with a very sustainable economy and a sustainable power system that is reliable.
Hey, what do you see as solutions? You mentioned that certainly the sun doesn't shine in the middle of the night, and perhaps if there's a pressure inversion that the wind isn't blowing, and you mentioned, well, then you have to have some sort of traditional or at least some kind of backup energy source. Maybe that storage, or maybe it's some other kind of traditional generation. What are your thoughts on the balance of that? Because Texas saw some challenges certainly when wind turbines weren't spinning, and they had actually some challenges with the traditional generation source, the gas turbines down there. So what are your thoughts then on what is the right balance between renewables and traditional dispatchable energy sources, right? You could go to the extreme and say you need, for every megawatt of wind, you need a megawatt of a gas turbine or something like that. And just from an economic standpoint, that seems really, really expensive. It's like, why not just have the gas turbine? Because it's always dispatchable versus the wind turbine.
Yeah, I don't have an exact answer for that. I think, and being in academia, we hear a lot on academic arguments of this, certainly, where there are some supportive of the centralized system. We have a traditional nuclear plant or a gas turbine plant or coal that is the backbone. But there are those as well that are going toward, well, if you're going to go toward a more healthy environment for all of us, that we need to implement these alternatives. And yes, it may have an additional cost associated with it, although the costs of those, at least at the customer level, are becoming very attractive for industry and for residential. So I think I don't have numbers, but I think a healthy balance is necessary for that. I think there's numbers on the order of we're in 65 to 68% of our traditional now, and the rest are moving in, and probably there'll be a continued blend, but not that significant of change, maybe on the order of 10% more penetration of renewables, and I'm not sure much more than that.
So that'll lead me into my next question then, that we say, well, the 65% traditional, 35% renewable, and there'll probably be some balancing between those particular percentages. But given these changes in generation, will there be a need for new ways to manage the power system? Will there be, say, more local control, maybe more centralized control, both, or something maybe entirely different?
I think it's going to be kind of a blend of those. I think certainly as we move over toward, like we had started at the beginning, we had talked about, these lower power level units kind of taking over from the traditional larger scale. So as we move that and we put that, for example, in a distribution system, we have communities that have their own sources and manufacturing plants that have a new sources with wind and solar. So they're forming what are now called microgrids. I think associated with those microgrids, there's likely a need for more aggressive control, or maybe the word aggressive may not be the best, but maybe I would say informed control, where the models associated with those particular pieces of devices are incorporated as part of the control and the control making decisions. There's more knowledge from sensors now. Our rates of data transfer are higher. And so I think to make those reliable and effective, most effective, it will likely be a more advanced control, not throwing out what's been done in the past, but incorporating some modeling and intelligence associated with it to make better, optimized decisions, and to also enable things like contingencies, more advanced contingencies, dealing with extremes like you saw in Texas. Can you do something where you can do quicker black starts, where you go down because of a catastrophic event? Can we do something with our microgrids and control them in such a way that we can pop back up much more effectively? I think that's probably where we're heading, is developing controls to enable us to do that.
So that's an interesting concept when you talk about microgrids. I usually think of the microgrid then as sort of a defensive move, if you will. There's a problem with the bulk electric power system. I want to keep our factories up and running. I would island from the bulk electric grid, fire up our generators, and run our facilities in our microgrid. But sitting listening to you, maybe there's an opportunity then to replicate what utilities have done, working with each other, this mutual support, if you will, where there's some interties and utility A and utility B can wield power back and forth to each other based on whether their plants are up and running or not, lines are out of service. You could almost scale that down. It sounds like when I'm listening to you at some kind of microgrid level, where my microgrid could interact with, say, the university's microgrid, and we could support each other during challenging times, whatever they may be, weather or some equipment failures or something like that, which would require some unique, I think, or certainly some additional control that would allow those two entities, whether it's us and the university, to work together to keep as many lights on to plants or buildings or what have you as possible. Have you guys thought much about that? And maybe that gets into my next question following on to that. with all these changes, we're talking about microgrids and stuff. Do you see a need to change your course curriculum to provide students with the skills to create these next generation grids, whether they're microgrids or macrogrids or what have you?
Yeah, well, going to your first question, I think, yes, certainly we have considered that, and that the technologies are in all likelihood available to enable that. So coupling of these microgrids, these small community, quote, or industrial plant grids, and sharing at that level. I think that's feasible. I think the question that arises associated with that is, do people have the confidence that that system can withstand contingencies? And so where I think we're limited right now is we're limited that to do studies that would ensure that we're going to keep this system operational to the reliability levels that people are desiring takes quite a bit of work. It takes a lot of engineering. It's setting up test model cases and saying, okay, what happens if as all these things change? Are we still going to work effectively? And so I think one of the key challenges associated with this is, can we make that process of developing these microgrids and integrating them faster? Can we reduce the engineering time? And I think that leads to the question, can we use models there and develop controls with models included so that that engineering time can be greatly reduced? And indeed, that's a research area that we have been exploring here at Purdue, and I know others have as well worldwide. And I think that is where we may be one of the ways to be most effective. In terms of working with students, there's always a change. It's funny, that's academia, and of course, life is about change, and we see that within the power system, we have all of these changing components. We have solar, we have wind, they have new models, they have new ways to do that are representing their characteristics. And so we do have to continually update the curriculum to incorporate that. I think where we're going to be heading in the next 10 years that might be very interesting is this integration of the transportation network with the power grid. It's been so far somewhat loosely coupled, but with electric vehicles, with charging, and with people's desire for ubiquitous charging, there's a stronger and stronger coupling with that. And so being able to couple transportation system dynamics with power system dynamics, that's something we're looking at now, and I think will be a focus here for the coming decades. And so that's kind of an exciting aspect within our educational program as well.
Yeah, I'm excited. And I know we're going to have another podcast where we talk specifically about, I think that the new term I heard was mobile loads, right? The EVs, and that's going to be a fascinating topic, especially with the I guess the excitement from the public to have electric vehicles. And certainly there's from the technical side or the infrastructure side, there's going to be some challenges with broad deployment of mobile loads or electric vehicles or whatever we're going to refer to them as going forward.
Right.
So with that, we've got mobile loads, we've got new generation sources that are distributed all over the place. What do you see as important research areas for power system control, and why?
Yeah. I think right now, certainly the power system control we're considering are these microgrid. How do you set up microgrids and control them and share assets between them and do that very effectively? And so setting up the controls to enable that, I think, is at the forefront. I think it's challenging because there are many dynamics that aren't in the traditional power grid necessarily, where you have power electronics. Things can respond and be controlled very rapidly. we're talking about on the microsecond level, millisecond level, in that range. So much faster than what we're typically associated with. And then heading toward that, I do believe, and I think we're seeing this here, right, in Texas and other places where there are extreme climate events. And we are, in all likelihood, going to have to deal with more and more chaotic systems in terms of weather. And so how do we deal with setting up grids or these microgrids that we may have to deploy or change how we deploy faster and more rapidly? And I think that's kind of at the cornerstone of what we've been focusing on lately.
Hey, Steve, what are specifically the challenges then with microgrids? You know, for a long time we've set up little small electrical systems, and now we have the benefits of power electronics, like you were saying there, right? They can respond in the order of microseconds. That's probably their processing is probably happening in a microsecond, but probably the output or the response is probably in the millisecond
right
time frame. But what do you see as the real challenge with these microgrids from a research perspective?
Yeah, I think the challenge, and people have addressed this, that in the traditional grid, you have these large rotating masses, meaning you have electric generators, they have a lot of steel, and they're rotating, so they have a lot of inertia. And we're trying to hold things, for example, at 60 hertz. With a power electronic-based microgrid, your inertia is less. You have to do this. You have to hold that 60 hertz, for example, by doing some dynamic control in the event of any change in your system. So that's one of the key challenges. And the other key challenge is you may not be, presently at least, you may not know all of the information about who's generating onto your system and what their associated dynamics are. So you didn't necessarily set up a model to predict exactly how the system's going to respond. So ensuring that your system is robust to a whole network of contingencies is probably one of the bigger challenges.
When you talk about the big spinning mass, I like to think of it as that big J, if you will, right? In the swing equation, where you have your mechanical power coming in minus your electrical power going out, and what makes up that difference for any of those changes is that big J and the change in frequency, if you will. And so as J gets really, really small, in fact, it's probably made up of, whatever the energy stored in capacitor is now, right? I think they call it synthetic energy, which I don't quite understand, or maybe I don't like the term. But that's what you have to be worried about, is that synthetic energy, or that J gets smaller and smaller, then the frequency is going to change a lot more for any disruption or imbalance between that mechanical energy and the electric energy. And that I can see that being a huge control problem, right? The time constant are going, from really, really long to really, really small with the twitchiness of these things. Exactly.
But, there are some alternatives, like we've thought of AC, right, for the last 100 years, but maybe the time has come to think of DC, not just for our high voltage tie lines, but looking at things in a DC distribution system. And maybe you make that last AC transition once you hit the meter or just before. That's things like that, I think, are being set up and considered now with the emergence of power electronics and more advanced controls.
Yeah, especially the way that the power electronics just beat up a 60 hertz sine wave, right? With where they like to siphon off a little bit of current. I think if you look at a distribution system right now, that it does not look like a sine wave if you're measuring the current anyway. They're horrible. So maybe DC is the right way to go in the future, which I'm sure would be another great podcast for us to sit down and talk about at some point. One final question for you on this topic is where What is Purdue working on right now? What do you certainly in the realm of power system control? What are you guys thinking about? What gets you excited these days?
Well, it is the power system control. We've been doing quite a bit of work on model predictive control. So trying to take, for example, the Schweitzer blue boxes and putting some intelligence. Well, there's already plenty of intelligence, but adding models into those components so that we can, for example, have a better system that's more responsive to contingencies, that stays healthy in the presence of contingencies that are relatively significant. Where, for example, now the way the system or a system is often operated is with traditional proportional, integral, derivative type controls. Trying to consider, when they set those up, the engineers did a phenomenal job, but they really couldn't tune those controls for the whole host of environments the system was going to see. And trying to improve the performance of the system by saying, okay, we now have a model and we're going to embed that intelligence in here and make decisions based on our sensor input that accounts for what we see the system doing. That's our focus effort right now, or a large focus effort in trying to get that so that the models are robust and fast enough to make those decisions and come up with more optimized systems. That's been at our forefront lately.
That is some exciting stuff. Predictive control always got me excited as a student, and it's really cool to see Purdue and your folks working along with some of our folks really taking that head on. I am convinced that is the future for power system control.
We agree.
I'm going to stay tuned on where you guys end up with being able to do that. Steve, thanks very much. It's been a great session. I know we're going to talk a little bit more about electric vehicles on a future podcast, and I'm really excited to have that conversation. For today, thanks again. I appreciate all your input, insight, and we'll see where the power system heads in the future.
Thank you, Dave. It was an honor to be with you.
Thanks.
Thank you for stopping by Schweitzer Drive. Join us again as we learn about, explore, and celebrate electric power. For more information about the show, please visit selinc.com/Schweitzer Drive.